Hi friends, today we start lecture 16 and I'm going to discuss Reynolds number and also the phenomena of transition, which is essentially transition from laminar flow to turbulent flow. That's something very important in fluid dynamics. I'm Dr. Ranjan Ganguly. Now in our previous lectures we discussed about Mach number. Mach number was the speed of the body through air divided by speed of sound, and essentially the Mach number is used to classify flow into the compressible and incompressible flow regimes. So you saw that when Mach number is below zero point 0.3, we can say the flow is incompressible, and when Mach number is greater than zero point 0.3, we say it is compressible flow. Now there is one more important parameter known as the Reynolds number, and this is essentially used to determine whether a flow is viscous or not. So essentially we use the Reynolds number to classify flow between viscous flow and inviscid or frictionless flow. So the Reynolds number is defined as density into velocity into some reference length x divided by viscosity, and the infinite subscripts here simply mean that these are quantities with reference to the free stream value. So if the velocity of air is v, then we call it v infinity here. Now you can see that Reynolds number is actually a local property. So if we are at some distance x in a flat plate, typically x from the leading edge, then the Reynolds number at that point x is rho infinity v infinity into x by mu infinity, and of course a parameter of great importance for us is going to be the boundary layer thickness. We are going to see that the boundary layer thickness depends on the Reynolds number, and that's one of the reasons for the importance of the Reynolds number in laminar and turbulent flow. Now if we look at the Reynolds number very carefully, we'll see that two of these properties are fixed because rho of course is the density of air, so it's typically 1.225 kg per meter cube, and you would know it at whatever location you are at. Similarly, the viscosity is 1.7894 into 10 to the power minus 5 kg per meter second. So if these are properties of the medium in which you are in, then the Reynolds number is going to depend on the velocity of the body and the reference length. So depending on the size of the particular aircraft or flying vehicle you are dealing with and its velocity, the Reynolds number is going to be different. For example, it will be about 2 million for airplanes which are relatively small, 20 million for large ones such as the transports and the passenger planes which fly between continents and between large cities. It's about 100,000 for the small unmanned air vehicles, and for micro air vehicles it may range to 10,000 and so on. Now there are also regimes like very low speed Reynolds numbers and so on, which are essentially purely viscous flow regimes. So as you go from high Reynolds number to low Reynolds number, the impact of viscosity is going to go up. So that's something you can see from this equation here. So for laminar boundary layers, it has been determined using boundary layer theory that the thickness of the boundary layer is given by 5.2 x by root of Reynolds number at the point x. And if you substitute Rex from here into this equation for delta, you can see that delta, which is the thickness of the boundary layer for a laminar boundary layer, is proportional to x to the power half, or essentially it is parabolic. Now we can also easily get an expression for skin friction coefficient. So skin friction coefficient is divided just like pressure, or is determined just like pressure. So you have the shear stress here, you divide it by the dynamic pressure, and so we can get this particular value for Cfx, which is 0.664 by root of Reynolds number. And if we have this value, then from this equation here we can easily obtain the skin friction drag, that is tau of W, that is the given by 0.664 q infinity by root of Rex. So that's the skin friction. Now, if we come to turbulent boundary layer, here the expressions have essentially come from experiments because this is a very complex problem. There is not much theory behind it. And so we can say delta is 0.37x by Reynolds number to the power zero point 0.2. And so here we see that delta is proportional to the x to the power 4 by 5. And again here we can obtain an expression for CFX as 0.0592 by Reynolds number local value to the power zero point 0.2. Now, just to tabulate or write this information down in one slide, I have put here the laminar boundary layer thickness, the turbulent boundary layer thickness, and if we plot these two for a flat plate, we get profiles like this here. So essentially, the laminar boundary layer follows the x to the power half profile. The turbulent boundary layer follows x to the power 4 by 5 profile. So the blue lines here and the blue delta, these are for turbulent flow, and the red ones are for laminar flow. Now there is a very important phenomena which takes place, which is that the laminar boundary layer after some time typically transitions into a turbulent boundary layer. And so if we were to do an experiment with a flat plate, we will see that after a certain point known as the transition point, the laminar boundary layer would become a turbulent boundary layer. And this is a very important place or location because the drag values which are going to come from these two boundary layers are going to be different, and that's going to play a big impact in determining how much drag is produced by the flight vehicle and what is the level of power which the aircraft must have in order to counter that kind of drag. So this particular location point is very important, and where it happens is known as the transition point, and we define it as X critical. So X subscript CR is that particular location on the flat plate where the transition from laminar boundary layer to turbulent boundary layer takes place. Now we can essentially write something known as a critical Reynolds number as follows. So this is the Reynolds number where x is xcr. So we take the value of x corresponding to the transition point, we put it in the equation for Reynolds number, and we are able to obtain the critical Reynolds number. Now we are going to look at some practical aspects of the Reynolds number in terms of pressure distribution and airfoil design. So before we do it, let's define a few properties. So if we were to take an airfoil section, let's say it has some chord given by C, and let's say the pressure at the top surface is P, then we can define a non-dimensional quantity known as the pressure coefficient, that is Cp, and that is P minus P infinity by Q infinity. So essentially here, of course, the values which have the subscript infinity correspond to the values in the free stream. So rho is the density, P is the pressure, and V is the velocity. So I can see by looking at this definition that both the numerator and the denominator have the units of pressure, which is Newton per meter square or Pascal, and therefore this is a non-dimensional quantity. So if I were to look at the typical CP distribution for a conventional airfoil, now you'll see that most conventional airfoils have a maximum thickness somewhere around the quarter chord region, or where essentially the X value is C by 4. So at this region you will get the minimum pressure also, which I have put in this blue dot here. So if we were to plot CP, it would come down like this and then go up here. This is a typical conventional airfoil type of situation. But if I were to plot the same CP on a laminar flow type of airfoil, then the CP variation would be something like this, and the minimum pressure would be at some point quite distant from the leading edge. So essentially what this would do is that this would create laminar flow for most of the airfoil cross section, and for laminar flow airfoils the maximum thickness is somewhere at the center of the particular wing section we are dealing with. Now laminar flow airfoils would keep the boundary layer or the flow laminar for a long period of time, But do remember that if there are any kind of discrepancies or any manufacturing defects or any corrosion on top or bottom of the whole airfoil section here, then that would have deleterious consequences for this particular type of airfoil section. But there are certain situations, certain flight vehicle where a laminar flow airfoil may actually be useful. So just to summarize today's talk, what we had here was that the Reynolds number is a good measure of the viscous effects on the flow, and also we saw that for different type of aircraft the Reynolds number is a good way to figure out at what flight regime you are at and how much is the effect of viscosity. Also, we saw that the boundary layer thickness is related to the Reynolds number. For laminar boundary layer, it is proportional to x half. For turbulent boundary layer, it is proportional to x 4 by 5. And there is a point at which there is a transition from laminar to turbulent boundary layer, and corresponding Reynolds number is known as critical Reynolds number, and that's given by rho infinity v infinity xcr mu infinity, where xcr is the point at which the transition takes place. So very often what happens is that if we have the critical Reynolds number, we can actually calculate the point where the transition takes place for a particular type of flow. So today's lecture introduced you to a very important number, that's the Reynolds number. It's like the brother of Mach number as far as aerodynamics is concerned. So whereas Mach number deals with compressibility, Reynolds number deals with viscosity and viscous flow. And we also saw that at different flight regimes or at different scales and speeds, the Reynolds number for different type of flight vehicles are different, and so the importance of the viscous effects becomes more as the Reynolds number become less. So for example, if you are dealing with micro air vehicles or small vehicles, the effect of viscosity is going to be more. And if you are dealing with very large airplanes which have Reynolds numbers in the millions, then the effect of viscosity is going to be less. So these are certain things we need to keep in mind whenever we are designing, especially aircraft such as micro air vehicles, unmanned air vehicles, and so on, which are becoming more and more popular and ubiquitous nowadays as far as aerospace engineering is concerned. So I'll end this video now and I will see you in a lecture sometime soon. See you then.